Okay, so for radiographic science, we want to make sure we define the terms correctly. So radiography, right? The process of making radiographs, which are the recordings, these pictures, these images we take of the inside of the body. Radiography is a branch of modern science in medicine. So there's science, scientific practice. Medicine is a part of science, and we're a part of medicine. So the things that we do, we try to approach them from a scientific standpoint. Okay. What we mean by a scientific standpoint, what we mean by, doing science is things that are considered scientific are objective, observable, and demonstratable. Okay. We're going to try to talk about those three things, but let's briefly say what they are. What does it mean for something to be objective?
Purely fact.
Yeah, it's fact-based, right? So if I said, like, I don't know, the sky is blue, right? Is that an objective fact?
It's an observation.
It's an observation that I made, right? And would everyone likely agree on that observation?
Not today.
Not today, right? But, it's something that's observable and fact-based, right? If I said it's cold in here, right? Is that fact or not?
Check.
Well, you might say, no, I'm fine, right? I might say it's cold. You might say I'm fine. Someone else might say it's burning up in here, right? That's completely subjective, yeah, because our body temperatures vary and the way we perceive our environment is relative to our body temperature, right? So it's completely subjective. The temperature, and the temperature is an objective thing, right? It's 72 degrees in here. That's an objective fact. But you feel it being cold or hot or fine, that's subjective, right? Okay, so that's what we mean by objective. The opposite of objective, fact-based, is subjective, which is opinion-based, okay? What does it mean for something to be observable?
You gotta be able to see it.
Yeah, only sight?
Well, you gotta be able to prove it.
Yeah, so if I can hear something, have I observed it?
In some way, yeah. Auditory, yeah.
If I turn my Geiger counter on and it measures some radioactive decay of an atom, right? Did I observe that?
Yeah.
Yeah, right. Because my device is a detecting device, a sensing device, and that sensing device told me that something had happened. Right. That's observable, even though I didn't see the atom radioactively decaying. My observation was done with the device. That device told me what was up, and I have an observable thing, and it can be repeated, right? So observation just has to be detectable with the human senses, okay, as well as the aid of equipment and things like that. So lots of observations in science are done, not directly with the human senses, but with equipment that sort of amplifies our senses, like something like a Geiger counter. And demonstratable. Demonstratable just means that, if I learn something about the world, I need to be able to share that information with the world, right? I can't have something happen and tell you it happened and then not be able to show it again, right? I should be able to show what had happened again, right? If I come running in the room and I say, guys, I threw a ball up into the air and instead of falling down like it normally does, it just took off into space. And they go, prove it, right? Hang on, let me go get another ball. I do it again, I throw the ball up and it falls right down, right? I'm just lying, right? I don't have demonstratable knowledge, right? It might have very well happen, right? But if I can't demonstrate it again to somebody, if I can't repeat the experiment, yeah, then it's not demonstratable knowledge and it's not science. Okay, so those are some things that make science science. We have objective things based in fact that are observable, and we can demonstrate and repeat these things that we do and see and learn. All right. Next, we'll learn some of these foundational principles that help guide us on our path through learning about the world. One of these principles is called parsimony. For something to be parsimonious, it needs to be simple, okay? So this is usually in relation to the way we give explanations about why things happen, okay? If you look up in the sky on any given night, you can usually see planets, right? They're the ones that look like stars but don't twinkle, okay? Back before we knew that planets moved in ellipses, okay, we came up with all sorts of goofy explanations for why the planets seemed to move. By the way, the word planets comes from a Greek word planetes, which means the wanderers, because these were like stars in the sky that moved around, right? Stars in the sky don't move around, but the planets do, okay? Anyways, we saw these things. You know, we can observe them with the naked eye. You don't even need a telescope to see that there's planets up there, to see there's something up there that's moving in the sky, right? And before we knew that we were the center of that the sun was the center of the solar system, and we orbited around the sun, and all the planets orbited around the sun as well, in ellipses, like we learned, we made up all kinds of crazy explanations for what was going on, right? We had explanations of planets moving in circles, and then moving in little mini circles in their orbits, right? To explain why sometimes in the sky we see planets go this way and back the other direction, retrograde. You probably heard about like Mercury going into retrograde, right? That literally just means Mercury was moving this way in the sky and then started moving the other direction in the sky, retrograde. We made all kinds of complicated explanations for these phenomena that we observed, right? Turns out that the right answer was the simple one, just that planets moved in ellipses and the sun was at the center, right? The Earth was not the center of the solar system. Nothing orbits around us. We orbit around it. Well, the moon does, but we orbit around everything. The sun and all the other planets orbit around it as well. We learned that the simple explanation was the correct one. So this is sort of a foundational principle of science, that given all of the possible explanations for something you see happening, the simple answer is usually the right one, okay? Or at least you should start by assuming that the simplest answers are the correct ones, right? So if there's two possible answers that you can think of for what's something you see happening, it's usually best to assume the simple answer is going to be correct and approach from that way rather than approaching from some complicated explanation. It has served well for most people. Now, sometimes answers are complicated, but we start with this foundational principle that we should consider simple explanations to be more likely. This is sometimes called Occam's razor, named from somebody named Sir Willem of Occam. This is a long time ago. He lived in the 13th and 14th century, I believe. And so, long time ago, this is the 12 and 1300s. Okay, this is 300, he died like 300 years before Isaac Newton was even born, okay? And you guys probably have heard of Isaac Newton. He's the creator of basically the modern physics that we have, okay? This guy's 300 years before that, so this is pre-scientific. And he said something, wait, what do we got? Oh, did you bring all that? You didn't have to bring all that in. Thank you.
And then I give this to the listeners here, evaluations.
Well, thank you.
There you go, thank you.
Okay. It's just notes and then evaluations. Don't get too scared. So this guy, Willem of Occam, said something to the effect of, and his words were, entities must not be multiplied beyond what is necessary. Basically what he's saying is keep it simple, stupid, right? He's saying the simple explanation's the likely thing, and he didn't call this idea Occam's razor. I think it took like 100 or so years for people to start referring to it as that. But the idea is, what do razors do? Shave, right? And the idea is Occam's razor is use Occam's razor to shave away all the unnecessary BS from your theory, and you're left with the simplest possible answer. Occam's razor. Okay, so when you're thinking about explanations for why things are happening, it's usually the simplest version of the answer that you should consider first. All right, other concepts in science. This sort of goes back to demonstratable knowledge from before. Reproducibility. Some experiment should be able to be duplicated by different people at different times in different locations and get the same results, right? We do experiments in the X-ray room where we do things like make an exposure on a body part, and then we change the mass, change the quantity of X-rays produced. Like we double it, we double the mass, right? What do we usually observe when we increase mass from one image to the next? What is the image? How does the image change? Contrast shouldn't change as long as you're not changing KVP. The image should get darker though, right?
Well, I'm not sure which one we were changing, but there was a couple times this week where a little heavier set patient just came out almost all white, and so we increased the mass.
Oh, good.
And it made a difference.
Oh, good. So at extreme ends of underexposure and overexposure, contrast is affected. But in the normal, like if you had a normal exposure, a normal happy exposure, right? And then you did that same exposure again, but doubled the mass. What do you expect to happen? How do you expect the image to change?
I'm not quite sure.
So more X-rays hitting the detector makes the image
More detail?
darker or lighter? Darker, right? More X-rays hit the detector, more exposure, the image gets darker, right? This is objective, right? If I double the mass, I have doubled the number of X-rays produced, right? And on my machine, when I double the mass, I double the number of X-rays produced, my image gets darker, okay? Take that same, all that same information, go to any other X-ray machine anywhere in the world, right? Do the same experiment. Take an image, get a nice happy X-ray, take another image with double the amount of exposure, the image is going to get darker, right? That's reproducible. I can take that experiment and take it anywhere in the world. I can do it today here and then tomorrow in, rural China, right? And I can do that same experiment. It's going to give me the same result, yeah? I should be able to do that with every scientific result, okay? Any experiment that you hear about should be reproducible, okay? And then since, we do pretty simple stuff here, but these simple things are reproducible. That's part of what makes them scientific. You should be getting the same results too. If the image gets twice as dark, with whatever change you made, you should be able to make that same change somewhere else and make that other image twice as dark, okay? All right, that's good. That's reproducibility. If you can't reproduce it, can't reproduce a result, it's not really scientific. You might get a cool answer one time, a cool result one time because of maybe, technical error or human error, right? But if you can't reproduce the result, then we don't call it science. All right, this next one is actually kind of hotly contested nowadays in modern science, but I'll give it to you in its original form and say it like I'll act like we just go with this now, even though this is pretty hotly contested nowadays. This next idea is falsifiability, okay? This is the idea that, and let me read from here and see if you can tell me what you think this means, then I'll maybe try to rephrase it. So falsifiability is saying a theory should be able to be proven, should be able to logically and logistically be proven false. What does that mean? Everyone's trying not to make eye contact with me, so I don't call on them. What does that mean? There's no wrong answers here.
If you have an idea, you have to prove that it's true or false, and then, I think everyone would have to agree.
Okay,
Yeah.
good. Let me give you one that's pretty. Give you an idea that is not falsifiable, and see if you can tell me why it's not falsifiable. I don't care regardless if you believe in some higher being or not. If I said God does not exist, okay? Or if I said God does exist, let's go with God does exist, okay? There's a God, doesn't matter, I'm not no specific religion, but if I said there's a God, is that a falsifiable statement?
Well, you can't prove it.
Right.
Yeah.
If I say there's a God, what would you have to do to falsify that?
Show me a God.
Show me a God or
Right.
prove to me that there's not one, right? You can't falsify that, right? There's been no direct, anything coming down and saying, hey, I'm God right here, right? I can't falsify that, yeah? That's a non-falsifiable statement. That's why it's not scientific. That's one big reason why science and religion are so split, okay? Because, religious things are completely based in what? How do you... Belief, right? You believe that it's true. No one's proven anything to you. You believe it, right? Totally based in belief, okay? That's what falsifiability is, okay? Scientific statements need to be able to be proven false. Now, that doesn't mean if somebody says something's true about the world, doesn't mean you have to go out and prove it false. It means that in principle, you can do an experiment and either continue to believe the thing is true based on the results of the experiment or prove it false, okay? So if I say, the goofy example they give in the textbook, if I say the moon is made of green cheese, okay? Is that falsifiable? Yeah, right? What do you have to do to falsify what I just said?
You have to prove what the moon was made out of.
Go to the moon, get some moon stuff, and bring it back to me, right? Show me that it's not green cheese, right? If I say Albert Einstein's the greatest physicist of the 20th century, is that falsifiable?
It's opinions.
It's completely opinion-based, and you can't do any experiment to prove me right or wrong, right? So it might be that a lot of people consider Albert Einstein to be great and maybe the greatest physicist. Not really. Probably not, right? But that's completely based in opinion, right? There's no experiment you can do to prove it one way or the other. So it's not falsifiable. It's not a scientific statement.
Like, but
He has hand up first. I'll go to you next.
sorry, but how come like during COVID, people were saying, okay, you can get it, and there's so many people say no, you can't get it, and there was X amount of science involved
Yeah.
on the vaccine, but there was some people who still believe it's the flu, and you know, it's just like they never proved that one completely wrong.
No, they did not. I would say I'm not sure to approach that, but I would say that there is a lot of anti-scientific sentiment in this country in general, and a lot of feeling like you shouldn't believe what science is telling you because it's sort of they're not so open with their way they collect data, the way they come to their opinions and things like that. So you get a lot of people that aren't willing to jump on board with what science is saying, I think. But and then another problem was they flip-flopped on their opinion. Scientific opinion changes, right? And people want science to be completely yes or no. We figured this out or we didn't figure this out, right? They don't want us to say we figured this out and then 2 weeks later to change our minds, right? That's how science has to work, right? We learn new things. We adjust our understanding based on what we learn, right? And that was a big problem at the beginning of COVID. And that really made for a lot of distrust from that point forward in what the scientific minds were saying. But this is a big one in science, falsifiability. It's sort of being very highly contested in a lot of things. So there are some things that are scientific ideas that we can't necessarily falsify. But let me leave it at that. Falsifiability is big.
Like,
Yeah, sorry, you had something to say.
The scientific method, right?
One more time.
The scientific method.
Yeah, falsifiability is a big part of the what we would call the scientific method. Yeah. All right, these next two, observation and measurement. Okay. Some experiment that we do should be able to be observed, right? Either directly or indirectly with the human senses. Like when we go into the X-ray room and we make X-rays, we take images, we make images of the body with our little experiments we're doing. We're observing the results immediately, right? We're getting some understanding from observing those results directly with our human senses. We're looking at the results on the screen, right? Same thing when we take like some radiation measurement, right? We're not directly observing the radiation, but we're getting information. We're observing information from our detecting device. So we're allowed to use devices to amplify our human senses, like Geiger counters and so forth. And then measurability. Results should be able to be measured and mathematically quantified. So, you got to be able to, go back to the example with mass, right? We can quantify how much mass you're using in an exposure. We can quantify how much that increases the exposure. We can even do things like get a pretty good idea of how many ionizing events are going to happen from that exposure. We can quantify what we're doing. That's what we mean to be measurable. We've got other measurements too, like our exposure deviation. That's a measurement. When we make an image, if you don't know, you haven't taken images yet, but when we take an image, we get a result on the screen, we get our image on the screen, and we get a number associated with that image. It tells us, measures exposure. Are we high? Are we low? Are we right where we should have been? Right with the expected value. That's a measurable thing. We get that with every image, and that's important to have that result because then we can use that to adjust our technical factors. For example, we can increase or decrease on the next and following images. So that's the idea. All right, so the scientific approach is really all of those things. If you do this all correctly, science is supposed to be self-correcting. We make mistakes, we get things wrong sometimes, right? That's what's really great about science is that, if you prove some result, if you do some experiment and get a result and say, this is how the world works, all of the other scientists are gonna, well, for one, there's gonna be a scientific consensus. Do we all agree with that result, right? But then it's full employment for all the other scientists to go and now try to falsify your result. Right? They're going to make it big. They're going to get well known if they take your result that's world changing and they falsify it, right? If they do some experiment to prove that your result was wrong, right? that's all the other scientists out there are going to now try to prove you wrong, okay, and thereby getting their own result, okay. This self-correcting nature makes it so that science, chugs ever so slowly towards the right answers. Okay, we get wrong answers here and there, but the whole scientific community should always be sort of working towards, the correct answers by having this falsifiable, self-correcting method. All right, so radiography as a branch of science includes a quantifiable amount of useful details, a measurable amount of information, including things like image qualities, positions, repeat rates. The standard of practice for radiographers is to use common sense, sound judgment, logical consistency, and objective knowledge to provide the best possible care for our patients. So we try to put these things into real practice for our patients.